So we can get started. Any questions before we get started? Yes, ma'am.
So in the breaks, none of the breaks.
They're still not showing up. I'll make sure they show up. Thank you for bringing that to my
A few
attention.
of them are still like they.
Okay. Yeah, connect this. I've had so many problems with it, but I'm this time going to
I'm
make
just
sure.
worried.
No.
Maybe just throw something.
No. There's no way they could be zeros. I have the statistics on them actually. I was on Connect yesterday. So the average was really high. This week, the only work we have to do is chapter 8 homework. That's it. There's just one homework on Connect. It's already there. So you have to do only the chapter 8 homework. Don and Austin, just chapter 8 homework. That's all there is this week. Okay, with that said, let me start the video. Tonight's topic is one of the most important topics in all of statistics. And the reason for that is at the beginning of the 20th century, all theories in statistics that were developed were basically based on the nice behaving normal distribution. But then there are variables and processes that don't obey the normal distribution. So then the question is can we still use the normal distribution theory for processes that are not normal? One non-normal process is incomes, for example. They're right skewed. They don't have a nice bell shape. Okay? So then they came up with this celebrated result called the central limit theorem. So they started studying the distributions of different statistics from which, they were basically asking, can I take my data, transform it, make it normal? It turns out, yes, you can do that. If you just took sample averages or sample proportions, actually they are guaranteed to be normal in large samples. Okay, that's what we call the central limit theorem. So let me start this, and then we'll play all the videos and the rest of the details in sequence.
Talk about what is easily one of the most fundamental and profound concepts of statistics, and maybe in all of mathematics. That's the central limit theorem. Central limit theorem. And what it tells us is we can start off with any distribution that has a well-defined mean and variance, has a well-defined variance, has a well-defined standard deviation. And it can be a continuous distribution or a discrete one. I'll draw a discrete one because it's easier to imagine for the purposes of this video. So let's say I have a discrete probability distribution equation, and I want to be very careful not to make it look anything close to a normal distribution, because I want to show you the power of the central limit theorem. So let's say I have a distribution. Let's say I can take on values 1 through 6, 1, 2, 3, 4, 5, 6, some kind of crazy dice. That's very likely to get a 1. Let's say it's impossible to get a straight line. You're very high likelihood of getting 1. Let's say it's impossible to get a 2. Let's say it's okay likely of getting a 3 or a 4. Let's say it's impossible to get a 5. Let's say it's very likely to get a 6 like that. So that's my probability distribution function. If I were to draw a mean, this is symmetric, so maybe the mean would be something like that. The mean would be halfway, so that would be my mean right there. The standard deviation would be that far and that far above below the mean. But that's my discrete probability distribution function. Now what I'm going to do here, instead of just taking samples of this random variable described by this probability distribution function, I'm going to take samples of it, but I'm going to average the samples and then look at those samples and see the frequency of the averages that I get. When I say average, I mean the mean. Let's say let me define. Let's say my sample size. I can put any number here. Let's say first off, we try a sample size of n is equal to 4. And what that means is I'm going to take 4 samples. So let's say the first time I take 4 samples. So my sample size is 4. Let's say I get a 1. Let's say I get another 1. Let's say I get a 3, and I get a 6. So that right there is my first sample of sample size 4. I know the terminology can be confusing because this is a sample that's made up of 4 samples. When we talk about the sample mean and the sampling distribution of the sample mean, which we're going to talk more and more about in the next few videos, normally the sample refers to the set of samples from your distribution, and the sample size tells you how many you actually took from your distribution. But the terminology can be very confusing because you could easily do one of these as a sample. We're taking 4 samples from you. We have a sample size of 4. What I'm going to do is I'm going to average them. So let's say the mean, I'll be very careful when I say average, the mean of this first sample of size 4 is what? 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 6 is 11, 11 divided by 4 is 2.75. 2.75. That is my first sample mean for my first sample of size 4. Do another one. My second sample of size 4. Let's say I get 3, 4, let's say I get another 3, and let's say I get a 1. I just didn't happen to get a 6 that time. And notice, I can't get a 2 or a 5. It's impossible for this distribution. The chance of getting a 2 or 5 is 0, so I can't have 2s or 5s. So in this, for the second sample of sample size 4, my sample mean for my second, so my second sample mean is going to be 3 plus 4, 7. 7 plus 3 is 10, plus 1 is 11. 11 divided by 4, once again, is 2.75. Let me do one more, because I really want to make it clear what we're doing here. So I do one more. Actually, we're going to do a gazillion more. Let me just do one more in detail. So let's say my third sample of sample size 4, so I'm going to literally take 4 samples. So my sample is made up of 4 samples from this original crazy distribution. Let's say I get a 1, and a 6, and a 6. And so my third sample mean is going to be 1 plus 1 is 2, 2 plus 6 is 8, 8 plus 6 is 14, 14 divided by 4. 14 divided by 4 is 3.5. And as I find each of these sample means, so for each of my samples, of sample size 4, I figure out a mean. And as I do each of them, I'm going to plot it on a frequency distribution. This is all going to amaze you in a few seconds. So I plot this all on a frequency distribution. So I say, okay, on my first sample mean is 2.75. So I'm plotting the actual frequency of the sample means I get for each sample. So 2.75, I got it one time, so I'll put a little plot there. So that's from that one right there. And I got the next time, I also got a 2.75. That's a 2.75 there, so I got it twice. So I'll plot the frequency right there. Then I got a 3.5. So all the possible values, I can have a 3, I can have a 3.25, I can have a 3.5. So then I have a 3.5, so I'll plot it right there. But what I'm going to do is I'm going to keep taking these samples. Maybe I'll take 10,000 of them. So I'm going to keep taking these samples. So I go all the way to S, 10,000. I just do a bunch of these. What's going to look like over time is each of these, I'm going to make it a dot because I'm going to have to zoom out. So if I look at it like this, over time, still has all the values that it might be able to take on. 2.75 might be here. So this first dot is going to be, this one right here is going to be right there. That second one is going to be right there. And that one at 3.5 is going to look right there. But I'm going to do it 10,000 times. I'm going to have 10,000 dots. Let's say as I do it, I'm going to just keep plotting them. I'm going to keep plotting the frequencies. I'm just going to keep plotting them over and over and over again. And what you're going to see is, as I take many, many samples of size 4, I'm going to have something that's going to start kind of approximating a normal distribution. So each of these dots represent an incidence of a sample mean. So as I keep adding on this column right here, that means I kept getting the sample mean 2.75. So over time, I'm going to have something that's starting to approximate a normal distribution. And that is the neat thing about the central limit theorem. So the central limit theorem, this was the case for, so in orange, that's the case for n is equal to 4. This was for sample size of 4. Now, if I did the same thing with the sample size of 20, so in this case, instead of just taking 4 samples from my original crazy distribution, every sample, I take 20 instances of my random variable, and I average those 20, and then I plot the sample mean on here. So in that case, I'm going to have a distribution that looks like this. And we'll discuss this in more videos. But it turns out if I were to plot the sample, 10,000 of the sample means here, I'm going to have something that, 2 things. It's going to even more closely approximate a normal distribution. And we're going to see in future videos, it's actually going to have a smaller, well, let me be clear. It's going to have it's going to have the same mean. That's the mean. This is going to have the same mean. It's going to have a smaller standard deviation. So I should plot these from the bottom because it's kind of static. When you get one, another instance. But this is going to more and more approach a normal distribution. So the reality is, and this is what's super cool about the central limit theorem, as your sample size becomes larger, or you can even say as it approaches infinity, you really don't have to get that close to infinity to really get close to a normal distribution. Even if you have a sample size of 10 or 20, you're already getting very close to a normal distribution. In fact, about as good an approximation as we see in our everyday life. What's cool is we can start with some crazy distribution, right? This has nothing to do with a normal distribution. But if we have a sample size, this was n equals 4, but if we have a sample size n equals 10 or n equals 100, and we were to take 100 of these instead of 4 here and average them, and then plot that average, the frequency of it, we would take 100 again, average them, take the mean, plot that again. And if we were to do that a bunch of times, in fact, if we were to do that an infinite time, we would find that, especially if we had an infinite sample size, we would find a perfect normal distribution. That's the crazy thing. And it doesn't apply just to taking the sample mean. Here we took the sample mean every time. You could have also taken the sample sum. The central limit theorem would have still applied. But that's what's so super useful about it. Because in life, there's all sorts of processes out there, proteins bumping into each other, people doing crazy things, humans interacting in weird ways, and you don't know the probability distribution functions, any of those things. What the central limit theorem tells us is that if we add a bunch of those actions together, assuming that they all have the same distribution, or if we were to take the mean of all of those actions together, and if we were to plot the frequency of those means, we do get a normal distribution. And that's frankly why the normal distribution shows up so much in statistics, and why, frankly, it's a very good approximation for the sum or the means of a lot of processes. Normal distribution. What I'm going to show you in the next video is I'm actually showing you that this is a reality, that as you increase your sample size, as you increase your n, and as you take a lot of sample means, you're going to have a frequency plot that looks very, very close to a normal distribution. The last video we learned about what is quite possibly the most profound idea in statistics. That's the central limit theorem. The reason why it's so easy is we start with any distribution that has a well-defined mean and variance. Actually, I made this standard deviation last week. That should be the mean. And let's say it has some variance. We write it like that, or I can write the standard deviation there. But as long as it has a well-defined mean and standard deviation, I don't care what the distribution looks like. What I can do is take samples, in the last video, say size 4. So that means I take literally 4 instances of this random variable. This is one example. I take their mean, and I decide to consider this the sample mean for my first trial, or you can almost say for my first sample. I know it's very confusing because you can consider that a sample, the set can be a sample, or you can consider each member of the set as a sample. So that can be a little bit confusing there. But I have this first sample mean, and then I keep doing that over and over. My second sample, my sample size is 4. I got 4 instances of this random variable. I average them. I have another sample mean. And the cool thing about the central limit theorem is as I keep plotting the frequency distribution of my sample mean, it starts to approach something that approximates the normal distribution. And it's going to do a better job of approximating that normal distribution as n gets larger. Just so we have a little terminology on our belt, this frequency distribution right here that I've plotted out, or here, or up here, that I started plotting out, that is called, it's kind of confusing because we use the word sample so much, that is called the sampling distribution of the sample mean. And let's dissect this a little bit just so that this long description of this distribution starts to make a little bit of sense. So when we say it's the sampling distribution, that's telling us that it's being derived from, it's a distribution of some statistic, which in this case happens to be the sample mean, and we're deriving it from samples of an original distribution. So each of these, so this is my first sample. My sample size is 4. I'm using the statistic, the mean. I actually have done with other names, the mode or the range or other statistics. The sampling distribution of the sample mean is the most common one. It's probably, in my mind, the best place to start learning about the central limit theorem and even, frankly, sampling distribution. So that's what it's called. And this is a little bit of background. I'll prove this to you experimentally, not mathematically, but I think experimental is on some of its more satisfying statistics, that this will have the same mean. This will have the same mean as your original distribution. As your original distribution right here. So it has the same mean. But we'll see in the next video that this is actually going to be, it's going to start approximating a normal distribution, even though my original distribution that this is kind of generated from is completely not normal. So let's do that with this app right here. And just to give proper credit is due. This is, I think it was developed at Rice University. This is from online statbook.com. This is their app, which I think is a really neat app because it really helps you to visualize what a sampling distribution of the sample mean is. So I can literally create my own custom distribution here. So let me make something kind of crazy. So you can do this in theory with a discrete or a continuous probability density function. But what they have here, we get on one of 32 values, and I'm just going to set the different probabilities of getting any of those 32 values. So clearly this right here is not a normal distribution. It's bimodal, but it doesn't have long tails. But what I want to do is first just use the simulation to understand or to better understand what the sampling distribution is all about. So what I'm going to do is I'm going to take, we'll start with 5 at a time. So my sample size is going to be 5. And so when I click animated, what it's going to do is going to take 5 samples from this probability distribution function. It's going to take 5 samples, and you're going to see them when I click animated. It's going to average them and plot the average down here. And then I'm going to do it again. So there you go. Got 5 samples from there, it averaged them, and hit there. What did I just do? I clicked. Oh, I want to clear that. Let me make this bottom one. So let me do that. So we take 5 at a time. So I took 5 samples from up here, and then it took its mean and plotted the mean there. Let me do it again. 5 samples from this probability distribution function, plotted it right there. I could keep doing it. It'll take some time. As you can see, I plotted it right there. Now, I can do this 1,000 times. It's going to take forever. Let's say I just wanted to do it 1,000 times. So this program, just to be clear, it's actually generating the random numbers. This isn't like a rigged program. It's actually going to generate the random numbers according to this probability distribution function. It's going to take 5 at a time, find their means, and plot the means. If I click 10,000, it's going to do that 10,000 times. So it's going to take 5 numbers from here 10,000 times and find their means 10,000 times, and then plot the 10,000 means here. So let's do that. So there you go. Notice it's already looking a lot like a normal distribution. And like I said, the original mean of my crazy distribution here was 14.45. And the mean of, after doing 10,000 samples or 10,000 trials, my mean here is 14.42. So I'm already getting pretty close to the mean there. My standard deviation, you might notice, is less than that. We'll talk about that in the future video. And the skew and kurtosis, these are ideas, these are things that help us measure how normal a distribution is. And I've talked a little bit about it in the past. And let me actually just diverge a little bit, just so it's interesting. And they're fairly straightforward concepts. Skew literally tells, so if this is a perfect normal distribution, really my drawing is very far from perfect. If that's a perfect distribution, this would have a skew of 0. If you have a positive skew, that means you have a larger right tail than you would have otherwise expected. So something with a positive skew might look like this. You would have a large tail to the right. So this would be a positive skew. Positive skew, which makes it a little less than ideal for a normal distribution. And a negative skew would look like this. It has a long tail to the left. So negative skew might look like that. So that is a negative skew. If you have trouble remembering it, just remember which direction the tail is moving. This tail is moving towards the negative direction. This tail is moving to the positive direction. So if something has no skew, that means that it's nice and symmetrical around its mean. Now, kurtosis, which sounds like a very fancy word, is similarly not that fancy of an idea. Kurtosis. So once again, if I were to draw a perfect normal distribution, remember, there's no one normal distribution. You can have different means and different standard deviations. Let's say that's a perfect normal distribution. If I have positive kurtosis, what's going to happen is I'm going to have fatter tails. I'm going to have fatter tails, but I'm going to have a more pointy peak. Then you draw that pointy peak. Fatter tails, and I'm going to have a more pointy peak than normal distribution. So this right here is positive kurtosis. So something that has positive kurtosis isn't, it's, you know, depending on how positive it is, it tells you it's a little bit more pointy than a real normal distribution. Positive kurtosis. And negative kurtosis has smaller tails, but it's smoother near the middle. So it's like this. So something like this would have negative kurtosis. Negative kurtosis. And maybe in future videos we'll explore that in more detail. But in the context of this simulation, it's just telling us how normal this distribution is. So when our sample size was n equal 5, and we did 10,000 trials, we got pretty close to normal distribution. Let's do another 10,000 trials just to see what happens. So let's see if it's more like a normal distribution. Our mean is now the exact same number. We still have a little bit of skew and a little bit of kurtosis. Now let's see what happens if we do the same thing with a larger sample size. We can actually do them simultaneously. So here's n equal 5. Let's do here n equals 25. So let me clear the sample distribution of the sample mean. And I'm going to run 10,000 trials. So I'll do one animated trial just to remember what's going on. So I'm literally taking first 5 samples from up here, find their mean. Now I'm taking 25 samples from up here, find its mean, and then plotting it down here. So here the sample size is 25, here it's 5. I'll do it one more time. I take 5, get the mean, plot it. Take 25, get the mean, and then plot it down there. This is a larger sample size. Now that thing that I just did, I'm going to do 10,000 times. 10,000 times. That's interesting. Remember, our first distribution was just this really crazy, very non-normal distribution. But once we get it, whoops, I didn't make it that big. But once we go up a little bit. So here, what's interesting? I mean, they both look a little normal, but if you look at the skew and the kurtosis, when our sample size is larger, it's more normal. This has a lower skew than when our sample size was only 5, and it has a less negative kurtosis than when our sample size was 5. So this is a more normal distribution. And one thing that we're going to explore further in a future video is not only is it more normal in its shape, but it's also tighter fit around the mean. And you can even think about it, why that kind of makes sense. When your sample size is larger, your odds of getting really far away from the mean is lower because it's very low likelihood to do 25 samples or 100 samples. If you're just going to get a bunch of stuff way out here, or a bunch of stuff way out here, you're very likely to get a reasonable spread of things. So it makes sense that your mean, your sample mean, is less likely to be far away from it. We're going to talk a little bit more about that in the future. But hopefully this kind of satisfies you that, at least experimentally, I haven't proven it to you with mathematical rigor, which hopefully will be in the future. But hopefully this satisfies you, at least experimentally, that the central limit theorem really does apply to any distribution. I mean, this is a crazy distribution. I encourage you to use this applet, that online stat book. I'm going to experiment with other crazy distributions and do it for yourself. And the interesting things are that we're approaching a normal distribution, but as my sample size got larger, it's a better fit for a normal distribution. We hopefully now have a respectable working knowledge of the sampling distribution of the sample mean. What I want to do in this video is explore a little bit more on how that distribution changes as we change our sample size and write that down, right? Our sample size. And so just as a bit of review, we saw before, we could just start off with any crazy distribution, something like this, on a discrete distribution. Really, to model anything, at some point you have to make it discrete. It can be a very granular discrete distribution. But let's say something crazy that looks like this. This is clearly not a normal distribution. What we saw in the first video, if you take, let's say, sample sizes of 4. So if you took 4 numbers from this distribution, 4 random numbers where, let's say this is the probability of 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you took 4 numbers at a time and averaged them, let me do that here. If you took 4 numbers at a time, let's say we use this distribution to generate 4 random numbers, right? We're very likely to get a 9. We're definitely not going to get any 7 or 8s. We're definitely not going to get a 4. We might get a 1 or 2. 3 is also very likely. 5 is very likely. So we use this function to essentially generate random numbers for us. And we take samples of 4, and then we average them up. So let's say our first average is like, it's a 9, it's a 5, it's another 9, and then it's a 1. So what is that? That's 14 plus 10, 24 divided by 4. The average for this first trial, for this first sample of 4, is going to be 6, right? The average 24 divided by 4. So we would plot it right here. Our average was 6 half time. Just like that, we'll just keep doing it. And we've seen in the past then if you just keep doing this, it's going to start looking something like a normal distribution. So maybe you do it again, the average is 6 again, maybe you do it again, the average is 5, you do it again, the average is 7, you do it again, the average is 6. And then if you just do this a ton of times, your distribution might look something that looks very much like a normal distribution. So these boxes are really small. So you just do a bunch of these trials. At some point, it might look a lot like a normal distribution. Obviously, there's some average values. It won't be a perfect normal distribution because you can never get anything less than 0 or anything less than 1 really as an average. You can't get 0 as an average. And you can't get anything more than 9. So it's not going to have infinitely long tails, but at least for the middle part of it, a normal distribution might be a good approximation. In this video, what I want to think about is what happens as we change n. So in this case, n was 4. N is our sample size. Every time we do a trial, we took 4 and we took their average and we plotted it. We could have had n equal 10. We could have taken 10 samples from this population, you could say, or from this random variable, averaged them, and then plotted them here. And in the last video, we ran the simulation. I'm going to go back to that simulation in a second. We saw a couple of things. And I'll show it to you a little bit more in depth this time. When n is pretty small, it doesn't approach a normal distribution that well. So when n is small, let's take the extreme case. What happens when n is equal to 1? That literally just means I take one instance of this random variable and average it. Well, it's just going to be that thing. So if I just take a bunch of trials from this thing and plot it over time, what's it going to look like? Well, it's definitely not going to look like a normal distribution. It's going to look, you're going to have a couple of 1s, you're going to have a couple of 2s, you're going to have more 3s like that, you're going to have no 4s, you're going to have a bunch of 5s, you're going to have some 6s that look like that, and you're going to have a bunch of 9s. So there, your sampling distribution of the sample mean for n of 1 is going to look, I don't care how many trials you do, it's not going to look like a normal distribution. So the central limit theorem, although I said, you do a bunch of trials and look like a normal distribution, definitely doesn't work for n equal 1. As n gets larger, though, it starts to make sense that, let's say, if I've got n equals 2, and I'm all just doing this in my head, I don't know what the actual distribution will look like, but then it still would be difficult for it to become an exact normal distribution, but then you can get more instances, you could get more, you might get things from all of the above, but you can only get 2 in each of your baskets that you're averaging, you only get 2 numbers, right? So you're never gonna, for example, you're never gonna get a 7.5 in your sampling distribution of the sample mean for n is equal to 2, because it's impossible to get a 7, and it's impossible to get an 8. So you're never gonna get 7.5 as, so maybe when you plot it, maybe it looks like this. There'll be a gap of 7.5, that's possible, and maybe it looks something like that. So it still won't be a normal distribution when n is equal to 2. So there's a couple of interesting things here. So one thing, and I didn't mention this the first time because I really wanted to get a gut sense of what the central limit theorem is. The central limit theorem says as n approaches really as it approaches infinity, then is when you get the real normal distribution. But in kind of everyday practice, you don't have to get that much beyond n equals 2. If you get to n equals 10 or n equals 15, you're getting very close to a normal distribution. So this converges to a normal distribution very quickly. Now, the other thing is you obviously want many trials. So this is your sample size. That is your sample size. That's the size of each of your baskets. In the very first video I did on this, I took a sample size of the size of 4. And some simulation I did in the last video, we did sample sizes of 4 and 10, whatever else. So sample size of 1. So that's our sample size. So as that approaches infinity, your actual sampling distribution of the sample mean will approach a normal distribution. Now, in order to actually see that normal distribution and actually prove it to yourself, you would have to do this many. Remember, the normal distribution happens. This is kind of the population. This is the random variable. That tells you all of the possibilities. In real life, we seldom know all of the possibilities. In fact, in real life, we seldom know the pure probability generating function, only from kind of writing a computer program. Normally, we're doing samples and we're trying to estimate things. So normally there's some random variable, and then maybe we'll do a bunch of, we take a bunch of samples, we take their means and we plot them, and then we're going to get some type of normal distribution. Let's say we take samples of 100 and we average them. We're going to get some normal distribution. And in theory, as we take those averages hundreds or thousands of times, our data set is going to more closely approximate that pure sampling distribution of the sample mean. This thing is a real distribution. It's a real distribution with a real mean. Its mean, it has a pure mean. Its mean, so the mean of the sample of the sampling, the mean of the sampling distribution of the sample mean, we'll write it like that. Notice I didn't write it as just the x. What this is actually saying this is a real population mean. This is a real random variable mean. If you looked at every possibility of all of the samples that you can take from your original distribution, from some other random original distribution, they took all of the possibilities of, let's say, sample size, assuming sample size is 10. If you took all of the combinations of 10 samples from some original distribution, you average them out, this would describe that function. Of course, in reality, if you don't know the original distribution, you can't take an infinite samples from it. So you won't know every combination. But if you did it with 1,000, if you did a trial 1,000 times, 1,000 times you took 10 samples from some distribution and took 1,000 averages and then plotted them, you're going to get pretty close. Now, the next thing I want to touch on is what happens is then, we know as n approaches infinity, it becomes more of a normal distribution. But, as I said already, n equals 10 is pretty good. N equals 20 is even better. But we saw something in the last video that at least I find pretty interesting. Let's say, we start with this crazy distribution up here. It really doesn't matter what distribution we're starting with. We saw in the simulation that when n is equal, let's say n is equal to 5, our graph, after we try, we take samples of 5, average them, we do 10,000 times, our graph looks something like this. It's kind of wide like that. And then when we did n is equal to 10, our graph, it was actually a little bit squeezed in like that, a little bit more. So not only was it more normal, but that's what the Central Theorem tells us, we're taking larger sample sizes, but it had a smaller standard deviation or a smaller variance, right? The mean is going to be the same in either case. But when our sample size was larger, our standard deviation became smaller. In fact, our standard deviation became smaller than our original population distribution. So our original probability density function. Let me show you that with the simulation. So let me clear everything. And this simulation is as good as any. So the first thing I want to show, or this distribution is as good as any. The first thing I want to show you is that n of 2 is really not that good. So let's compare an n of 2 to, let's say, an n of 16. So when you compare an n of 2 to an n of 16, let's do it once. So you have 1, 2 trials, you average them, then it's going to be 16. It's going to plot it down here and average there. Let's do that 10,000 times. So notice, when you took an n of 2, even though we did it 10,000 times, this is not approaching a normal distribution. You can actually see it in the skew in kurtosis numbers. It has a rightward positive skew, which means it has a longer tail to the right than to the left. And then it has a negative kurtosis, which means that it's a little bit, it has shorter tails and smaller peaks than a standard normal distribution. Now, when n is equal to 16, you do the same trick. So every time you took 16 samples from this distribution function up here and average them, and each of these dots represent an average. We did 10,001 times. Here, notice the mean is the same in both places, but here all of a sudden, our kurtosis is much smaller and our skew is much smaller. So we are more normal in this situation. But even a more interesting thing is our standard deviation is smaller, right? This is more squeezed in than that is. It's definitely more squeezed in than our original distribution. Now let me do it with two. Let me clear everything again. I like this distribution because it's a very non-normal distribution. It's a bimodal distribution of some kind. And let's take a scenario where I take an n of, let's take two good n's. Let's take an n of 16. That's a nice healthy n. Let's take an n of 25. Let's compare them a little bit. So let's just do one trial n. It's always nice to see it. The person's going to do 16 of these trials and average them, and there we go. And it's going to do 25 of these trials and average them, and then there we go. Now let's do that. What I just did, animated. Let's do it 10,000 times. Miracles of computers. Now notice something. This is 10,000 times. These are both pretty good approximations of normal distributions. The n is equal to 25 is more normal. It has less skew, slightly less skew than n is equal to 16. It has slightly less kurtosis, which means it's closer to being a normal distribution. 16. But even more interesting, we see that it has a lower standard deviation. The standard deviation here is 2.1, and the standard deviation here is 2.64. So that's another, and I kind of touched on that in the last video. And it kind of makes sense. For every sample you do for your average, the more you put in that sample, the less standard deviation. Think of the extreme case. If instead of taking 16 samples from our distribution every time, or instead of taking 25, if I were to take 1 million samples from this distribution every time, if I were to take 1 million samples from this distribution every time, that sample mean is always going to be pretty darn close to my mean. If I take 1 million samples of everything, if I try to estimate a mean by taking 1 million samples, I'm going to get a pretty good estimate of that mean. The probability that that a bunch of a million numbers are all out here is very low. So if n is 1 million, of course, all of my sample means when I average them are all going to be really tightly focused around the mean itself. And so hopefully that kind of makes sense to you as well. If it doesn't, just think about it, or even use this tool and experiment with it, just so you can trust that is really the case. And it actually turns out that there's a very clean formula that relates the standard deviation of the original probability distribution function to the standard deviation of the sampling distribution of the sample mean. And as you can imagine, it is a function of your sample size, of how many samples you take out in every basket before you average them. I'll go over that in the next video. We've seen in the last several videos. You start off with any crazy distribution. It doesn't have to be crazy, it could be a nice normal distribution, but to really make the point that you don't have to have a normal distribution, I like to use crazy ones. So let's say you have some kind of crazy distribution, something like that, like anything. But we've seen multiple times, you take samples from this crazy distribution. So let's say you were to take samples of, let's say n is equal to 10. So we take 10 instances of this random variable, average them out, and then plot our average. Plot our average. We get one instance there. We keep doing that. We do that again. We take 10 samples from this random variable, average them, plot them again, and eventually you do this a gazillion times, in theory, infinite number of times, and you're going to approach the sampling distribution of the sample mean. All right, n equal 10. It's not going to be a perfect normal distribution, but it's going to be close. It would be perfect only if n was infinite. Let's say we eventually, all of our samples, we get a lot of averages over there, it stacks up there, and eventually we'll approach something that looks something like that. And we've seen from the last video that if let's say we were to do it again, this time let's say that n is equal to 20. The distribution that we get is going to be more normal. In future videos, we'll delve even deeper into things like kurtosis and skew. It's going to be more normal, but even more importantly, or I guess even more obviously to us, we saw that in the experiment, it's going to have a lower standard deviation. So they're all going to have the same mean. Let's say the mean here is, let's say the mean here is 5. Then the mean here is also going to be 5. The mean of our sampling distribution of the sample is going to be 5. It doesn't matter what our n is. Our n is 20, it's still going to be 5, but our standard deviation is going to be less than either of these scenarios. And we saw that just by experimenting. Right? It's going to be more normal. It's going to have a tighter standard deviation. So maybe it'll look like that. And if we did it with a even larger sample size, color, if we did that with an even larger sample size, n is equal to 100, what we're going to get is something that fits the normal distribution even better. We take 100 instances of this random variable, average them, plot it. 100 instances of this random variable, average them, plot it. We just keep doing that. If we keep doing that, what we're going to have is something that's even more normal than either of these. So it's going to be a much closer fit to a true normal distribution, but even more obvious to the human eye. It's going to be even tighter, so it's going to be a very low standard deviation. It's going to look something like that. I'll show you that on the simulation app in the next, or probably later in this video. So two things happen. As you increase your sample size for every time you do the average, two things are happening. You're becoming more normal, and your standard deviation is getting smaller. So the question might arise, well, is there a formula? So if I know the standard deviation, so this is my standard deviation of just my original probability density function. This is the mean of my original probability density function. So if I know the standard deviation, and I know n is going to change depending on how many samples I'm taking every time I make a sample mean. If I know my standard deviation, or maybe if I know my variance, right? The variance is just the standard deviation deviation squared. If you don't remember that, you might want to review those videos. But if I know the variance of my original distribution, and if I know what my n is, how many samples I'm going to take every time before I average them in order to plot one thing, my sampling distribution of my sample mean, is there a way to predict what the mean of these distributions are? And so the standard deviation of these distributions. And so you don't get confused between that and that, let me say the variance. If you know the variance, you can figure out the standard deviation. One is the square root of the other. So this is the variance of our original distribution. Now, to show that this is the variance of our sampling distribution of our sample mean, we'll write it right here. This is the variance of our mean, of our sample mean. Remember, our true mean is this, that the Greek letter mu is our true mean. This is equal to the mean, while x with a line over it means sample mean. Sample mean. So here what we're saying is this is the variance of our sample means. Now this is going to be a true distribution. This isn't an estimate. There's some, if we magically do this distribution, there's some true variance here. And of course the mean, so this has a mean. This right here, we can just get our notation right. This is the mean of the sampling distribution of the sampling mean. So this is the mean of our means. It just happens to be the same thing. This is the mean of our sample means. It's going to be the same thing as that, especially if we do the trial over and over again. But anyway, the point of this video is there any way to figure out this variance, given the variance of the original distribution and your n? And it turns out there is. And I'm not going to do a proof here. I really want to give you the intuition of it. And I think you already do have the sense that every trial you take, if you take 100, you're much more likely, when you average those out, to get close to the true mean than if you took an n of 2 or an n of 5. You're just very unlikely to be far away, right? If you took 100 trials as opposed to taking 5. So I think you know that in some way it should be inversely proportional to n. The larger your n, the smaller standard deviation. It actually turns out it's about as simple as possible. It's one of those magical things about mathematics. I'll prove it to you one day. I want to give you a working knowledge first. In statistics, I'm always struggling whether I should be formal and give you rigorous proofs, but I kind of come to the conclusion that it's more important to get the working knowledge first in statistics. And then later, once you've gotten all of that down, we can get into the real deep math of it and prove it to you. But I think experimental proofs are kind of all you need for right now, using those simulations so that they're really true. So it turns out that the variance of your sampling distribution of your sample mean is equal to the variance of your original distribution, that guy right there, divided by n. That's all it is. So if this up here has a variance of, let's say this up here has a variance of 20, I'm just making that number up. Then let's say your n is 20, then the variance of your sampling distribution of your sample mean for an n of 20, well, you're just going to take the variance up here, your variance is 20, divided by your n 20. So here, your variance is going to be 20 divided by 20, which is equal to 1. This is the variance of your original probability distribution, and this is your n. What's your standard deviation going to be? What's going to be the square root of that? Right? Standard deviation is going to be the square root of 1. Well, that's also going to be 1. So we can also write this. We take the square root of both sides of this and say the standard deviation of the sampling distribution of the standard deviation of the sampling distribution of the sample mean is often called the standard deviation of the mean. And it's also called, I'm going to write this down, the standard error of the mean. Standard error of the mean. All of these things that I just mentioned, these all just mean the standard deviation of the sampling distribution of the sample mean. That's why this is confusing. If you use the word mean and sample over and over again, if it confuses you, let me know. I'll put another video or pause it, whatever. But if we just take the square root of both sides, the standard error of the mean, or the standard deviation of the sampling distribution of the sample mean, is equal to the standard deviation of your original function, your original probability density function, which could be very non-normal, divided by the square root of n. I just took the square root of both sides of this equation. I like to remember this, that the variance is just inversely proportional to n, and then I like to go back to this, because this is very simple in my head. You just take the variance divided by n. Oh, and if I want the standard deviation, I just take the square root of both sides, and I get this formula. So here, the standard deviation, when n is 20, the standard deviation of the sampling distribution of the sample mean is going to be 1. Here, when n is 100, our variance here, when n is equal to 100, so our variance of the sampling mean of the sample distribution, or our variance of the mean of the sample mean, we could say, is going to be equal to 20, this guy's variance, divided by n. So it equals, n is 100, it equals 1/5. Now, this guy's standard deviation, or the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean, is going to be the square root of that. So 1 over the square root of 5. And so, this guy's I'll have you, a little bit under 1/2 standard deviation, while this guy had a standard deviation of 1. So you see it's definitely. Now I know what you're saying. Well, Sal, you just gave a formula. I don't necessarily give you. Well, let's see if we can prove it to ourselves using the simulation. So I'll just for fun, I'll just mess with this distribution a little bit. So that's my new distribution. And let me take two things it's easy to take the square root of. We don't need standard deviation. So let's take an n of 16 and n of 25. And let's do 10,000 trials. So in this case, every one of the trials, we're going to take 16 samples from here, average them, plot it here, and do a frequency plot. Here, we're going to do 25 at a time, and then average. I'll do it once and so I'm taking 16 samples, plot it there. I take 16 samples, described by this probability density function, or 25 now, plot it down here. Now, if I do that 10,000 times, what do I get? All right, so here, just visually, you can tell this when n was larger, the standard deviation is smaller. This is supposed to be these together. But actually, let's write this stuff down. See if I can remember. Here, n is so in this random distribution I made, my standard deviation was 9.3. Remember these. Our standard deviation for the original thing was 9.3. And so standard deviation here was 2.3. And the standard deviation here is 1.87. Let's see if it conforms to our formula. So I'm going to take this off screen for a second. I'm going to go back and do some mathematics. So I have this on my other screen so I can remember those numbers. So in the trial we just did, my wacky distribution had a standard deviation of 9.3. When n is equal to, another color, when n was equal to 16, just doing the experiment, doing a bunch of trials and averaging all the things, we got the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean. We experimentally determined it to be 2.33. And then when n is equal to 25, we got the standard error of the mean being equal to 1.87. Let's see if it conforms to our formulas. So we know that the variance, or we could almost say the variance of the mean, or the standard error, the variance of the sampling distribution of the sample mean is equal to the variance of our original distribution divided by n. Take the square roots of both sides, then you get standard error of the mean is equal to standard deviation of your original distribution divided by the square root of n. So let's see if this works out for these two things. So if I were to take 9.3, so let me do this case. So 9.3 divided by the square root of 16, right? N is 16. So divided by the square root of 16, which is 4, what do I get? So 9.3 divided by 4. Calculator out here. Let's see if we have, let's figure it out. We want to divide 9.3 divided by 4. 9.3 divided by square root of n, and 16, so divided by 4, is equal to 2.32. 2.32. So this is equal to 2.32, which is pretty darn close to 2.33. This was after 10,000 trials. Maybe right after this, I'll see what happens. We did 20,000 or 30,000 trials. We take samples of 16 and average them. Now let's look at this. Here, we would take 9.3. Draw the line here. That might be better. So we take our standard deviation of our original distribution. So just that formula that we derived right here would tell us that our standard error should be equal to the standard deviation of our original distribution, 9.3, divided by the square root of n, divided by square root of 25, right? 4 was just the square root of 16. So this is equal to 9.3 divided by 5. Let's see if it's 1.87. calculator back. So if I take 9.3 divided by 5, what do I get? 1.86, which is very close to 1.87. We got in this case 1.86. 1.86. So as you can see, what we got experimentally was almost exactly, and this is after 10,000 trials, of what you would expect. Let's do another 10,000. So you got another 10,000 trials. Well, we're still in the ballpark. We're not gonna, maybe I can't look at the exact number, rounded or whatever. But as you can see, hopefully that'll be pretty satisfying to you, that the variance of the sampling distribution of the sample mean, the variance of the sampling distribution sampling mean, is just going to be equal to the variance of your original distribution, no matter how wacky that distribution might be, divided by your sample size, by the number of samples you take for every basket that you average. I guess is the best way to think about it. And sometimes this can get confusing because you are taking samples of averages based on samples. When someone says sample size, you're like, is sample size the number of times I took averages or the number of things I'm taking averages of each time? And it doesn't hurt to clarify that. Normally when they talk about sample size, they're talking about N. And at least in my head, when I think of the trials as you take a sample size of 16, you average it, that's one trial, and you plot it. Then you do it again, you do another trial, you do it over and over. But anyway, hopefully this makes everything clear. And then you now also understand how to get to the standard error of the mean. The average male drinks 2 liters of water when active outdoors, with a standard deviation of 0.7 liters. You are planning a full day nature trip for 50 men, and will bring 110 liters of water. What is the probability that you will run out of water? So let's think about what's happening here. So there's some distribution of how many liters of average man needs when they're active outdoors. And let me just draw an example. It might look something like this. So they're all going to need at least more than 0 liters. This would be 0 liters over here. The average male, so the mean of the amount of water a man needs when active outdoors is 2 liters. So 2 liters would be right over here. So the mean is equal to 2 liters. It has a standard deviation of 0.7 liters, 0.7 liters. So the standard deviation, maybe I'll draw it this way. So this distribution, once again, we don't know whether it's normal distribution or not. It could just be some type of crazy distribution. So maybe some people need almost close to, well, everyone needs a little bit of water, but maybe some people need very, very little water. Then you have a lot of people who need that. Maybe some people need more, and maybe no one can drink more than maybe it's like 4 liters of water. So maybe this is the actual distribution, and one standard deviation is going to be 0.7 liters away. So this is 1.7 liters this would be 1 liter, 2 liters, 3 liters. So one standard deviation is going to be about that far away from the mean. If you go above it, it'll be about that far. If you go below it, we draw this is the standard deviation. That right there is the standard deviation to the right. That's the standard deviation to the left. And we know that the standard deviation is equal to, I'll write 0.7 liters. So that's the actual distribution of how much water the average man needs when active. Now, what's interesting about this problem, we are planning a full day nature trip for 50 men and will bring 110 liters of water. What is the probability that you will run out? So probability that you will run out, let me write this down. The probability that I will or that you will run out is equal or is the same thing as the probability that we use more than 110 liters, use more than 110 liters on our outdoor nature day, whatever we're doing, which is the same thing as the probability. If we use more than 110 liters, that means that on average, because we have 50 men, so 110 divided by 50 is what? That's 2 point. Let me get the calculator out just so we don't make any mistakes here. So this is going to be calculator out. So on average, if we have 110 liters, it's going to be drunk by 50 men, including ourselves, I guess. That means that it's the problem. So that we would run out if on average more than 2.2 liters is used per man. So this is the same thing as the probability of the average, or maybe we should say the sample mean, or let me write it this way, that the average water use per man of our 50 men is greater than, or we say greater than or equal to, greater, let me say greater than, well, I'll say greater than, if we write on money, we won't run out of water, is greater than 2.2 liters per man. So let's think about this. We are essentially taking 50 men out of a universal sample, and we got this data. Who knows where we got this data from? And the average men is 2 liters, and the standard deviation is this. Maybe there's some huge study, and this is the best estimate of what the population parameters are. But this is the mean, and this is the standard deviation. Now we're sampling 50 men, and what we need to do is figure out essentially what is the probability that the mean of this sample, that the sample mean is going to be greater than 2.2 liters. And to do that, we have to figure out the distribution of the sampling mean. And we know what that's called. It's the sampling distribution of the sample mean. And we know that that is going to be a normal distribution. We know a few of the properties of that normal distribution. So this is a distribution of just all men. And then if you take samples of, say, 50 men, so this will be, let me write this down. So down here, I'm going to draw the sampling distribution. The sampling distribution of the sample mean when n, so when our sample size is equal to 50, when our sample size is 50. So this is essentially telling us the likelihood of the different means when we are sampling 50 men from this population and taking their average water use. So we draw that. So let's say that this is frequency, and then here are the different values. Now, the mean value of this, the mean, let me write the mean of the sampling distribution of the sample mean, this x bar, that's really just the sample mean right over there, is equal to, it's going to be equal to, if we were to do this millions and millions of times, if we were to plot all of the means when we keep taking samples of 50 and we plot them all out, we would show that this mean of distribution is actually going to be the mean of our actual population. So it's going to be the same value. It's going to be the same value as this population over here. So that is going to be 2 liters. So we're still centered at 2 liters. But what's neat about this is that the sampling distribution of the sample, so you take 50 people, find their mean, plot the frequency, 50 people, find their mean. This is actually going to be a normal distribution regardless of, this one just has a well-defined standard deviation mean. It's not normal. Even though this one isn't normal, this one over here will be. We've seen it in multiple videos already. So this is going to be a normal distribution. And the standard deviation, and we saw this in the last video, and hopefully we've got a little bit of information for why this is true. The standard deviation, actually, I'm going to put it a better way, the variance of the sample mean is going to be the variance. So remember, it's going to be, this is standard deviation. So it's going to be the variance of the population divided by n. And if you wanted the standard deviation of this distribution right here, you just take the square root of both sides. Take the square root of both sides of that. We have the standard deviation of the sample mean is going to be equal to the square root of this side over here is going to be equal to the standard deviation of the population divided by the square root of n. And what's this going to be in our case? We know what the standard deviation of the population is. It is 0.7. And what is n? We have 50 men. 0.7 over the square root of 50. Now let's figure out what that is with the calculator. So we have 0.7 divided by the square root of 50. And we have 0.09, I'll say 0.098. It's pretty close to 0.99. So I'll just write that down. So this is equal to 0.099. That's going to be the standard deviation of this. It's going to have a lower standard deviation. So it's going to look the distribution is going to be normal. It's going to look something like this. So this is 3 liters over here. This is 1 liter. 1 liter. The standard deviation is almost a tenth. So it's going to be a much narrower distribution. It's going to look something. Trying my best to draw it. It's going to look something like this. Something like this. You get the idea? Where the standard deviation right now is almost 0.1. So it's 0.09, almost a tenth. So it's going to be something. 1 standard deviation away is going to look something like that. So we have our distribution. It's a normal distribution. And now let's go back to our question that we're asking. We want to know the probability that our sample will have an average, greater than 2.2. So this is the distribution of all of the possible samples, the means of all of the possible samples. Now, to be greater than 2.2, 2.2 is going to be right around here. 2.2 is going to be right around here. So we essentially are asking, we will run out if our sample mean falls into this bucket over here. So we essentially need to figure out what's this area under this curve there. And to figure that out, we just have to figure out how many standard deviations above the mean we are, which is going to be our z-score. And then we can use a z-table to figure out what this area right over here is. So we want to know when we're above 2.2 liters. So 2.2 liters, 2.2, we can even do it in our head. 2.2 liters is what we care about. That's right over here. That is, our mean is 2. So we are 0.2 above the mean, And if we want that in terms of standard deviations, we just divide this by the standard deviation of this distribution over here. And we figured out what that is. The standard deviation of this distribution is 0.099. So if we take, and you'll see a formula where you take this value minus the mean and divided by the standard deviation. That's all we're doing. We're just figuring out how many standard deviations above the mean we are. So you just take this number right over here, divided by the standard deviation, so 0.099 or 0.099. And then we get our calculator. And actually, we get the exact number over here. So we can just take 0.2. We can just take this 0.2 divided by this value over here. On this calculator, when I press second answer, it means the last answer. So I'm taking 0.2 divided by this value over there, and I get 2.020. So that means that this value, or actually, right, this probability is the same probability of being 2.02 standard deviations. Maybe I should write it this way. More than, let me write it down here where I have more space. So this all boils down to the probability of running out of water is the probability that the sample mean will be more than just the 50 that we happen to select. Remember, if we take a bunch of samples of 50 and plot all of them, we'll get this full distribution. But the 150, the group of 50 that we happen to select, the probability of running out of water is the same thing as the probability of the mean of those people will be more than 2.020 standard deviations above the mean of this distribution, which they're actually the same distribution. So what is that going to be? Here we just have to look up our z-table. Remember, this 2.02 is just this value right here, 0.2 divided by 0.09. I just have to pause the video because there's some type of fighter jet outside or something. But anyway, hopefully they won't come back. But anyway, so we need to figure out the probability that the sample mean will be more than 2.02 standard deviations above the mean. And to figure that out, we go to a z-table, and you can find this pretty much anywhere. You should see any stat book or on the internet, wherever. And so essentially, we want to know the probability. The z-table will tell you how much area is below this value. So if you go to z of 2.02, that was the value that we were dealing with, right? At 2.02, it was, so you go for the first digit, we go to 2.0, and it was 2.02. 2.02 is right over there, right? So we had 2.0, And the next digit you go up here. So 2.02 is right over there. So this 0.9783, let me write it down over here. This 0.9783, I'm going to be very careful, 0.9783. That Z table did not, that's not this value over here. This 0.9783 on the Z table, that is giving us this whole area over here. It's giving us the probability that we are below that value, that we are less than 2.02 standard deviations above the mean. So it's giving us that value over here. So to answer our question, to answer this probability, we just have to subtract this from 1, because these will all add up to 1. So we just take our calculator back out, and we just take 1 minus 0.9783 is equal to 0.0217. So this right here is 0.0217, or another way you could say it is a 2.17% probability that we will run out of water. And we are done. Make sure I got that number right. So that number, it was at 0.2017, right? So it's a 2.17% chance we run out of water. It is election season, and there's a runoff between candidate A versus candidate B. And we are pollsters, and we're interested in figuring out, well, what's the likelihood that candidate A wins this election? Well, ideally, we would go to the entire population of likely voters, right? Let's say there's 100,000 likely voters, and we would ask every one of them, who do you support? And from that, we would be able to get the population proportion, which would be, this is the proportion that support candidate A. But it might not be realistic. In fact, it definitely will not be realistic to ask all 100,000 people. So instead, we do the thing that we tend to do with statistics is that we sample this population and we calculate a statistic from that sample in order to estimate the parameter. So let's say we take a sample right here. So this sample size, let's say n equals 100, and we calculate the sample proportion that support candidate. So out of the 100, let's say that 54 say that they're going to support candidate A. So the sample proportion here is 0.54. And just to appreciate that we're not always going to get 0.54. There could have been a situation where we sampled a different 100 and we would have maybe gotten a different sample proportion. Maybe in that one we got 0.58. And we already have the tools and statistics to think about this, the distribution of the possible sample proportions we could get. We've talked about it when we thought about sampling distributions. So you could have the sampling distribution of the sample proportions, And it's going to, this distribution is going to be specific to what our sample size is for n is equal to 100. And so we can describe the possible sample proportions and their likelihoods with this sampling distribution. Look at something like this. Because our sample size is so much smaller than the population, it's way less than 10%, we can assume that each person we're asking that it's approximately dependent. Also, if we make the assumption that the true proportion isn't too close to 0 or not too close to 1, then we can say that, well, look, the sampling distribution is roughly going to be normal. So we'll have a normal kind of bell curve shape. And we know a lot about the sampling distribution of the sample proportions. We know already, for example, and this is foreign to you, I encourage you to watch the videos on this, Khan Academy, that the mean of this sampling distribution is going to be the actual population proportion. And we also know what the standard deviation is. So that's one standard deviation, this is two standard deviations, this is three standard deviations. Above the mean, that's one standard deviation, two standard deviations, three standard deviations below the mean. So this distance, color, this standard deviation right over here, which we denote as the standard deviation of the sample proportions for the sampling distribution. This is, we've already seen the formula. It's the square root of P times 1 minus p, where p is once again our population proportion, divided by our sample size. That's why it's specific for n equals 100. And so in this first scenario, let's just focus on this one right over here. When we took a sample size of n equals 100, we got the sample proportion of 0.54. We could have gotten all sorts of outcomes here. Maybe 0.54 is right over here. Maybe 0.54 is right over here. And the reason why I have this uncertainty is we actually don't know what the real population parameter is, what the real population proportion is. So let me ask you maybe a slightly easier question. What is the probability that our sample proportion of 0.54 is within 2 times 2 standard deviations of p? Pause the video and think about that. Well, that's just saying, look, if I'm going to take a sample and calculate the sample proportion right here, what's the probability that I'm within 2 standard deviations of the mean? Well, that's essentially going to be this area right here. And we know from studying normal curves that approximately 95% of the area is within 2 standard deviations. So this is approximately 95%. 95% of the time that I take a sample size of 100 and I calculate this sample proportion, 95% of the time I'm going to be within 2 standard deviations. But if you take this statement, you can actually construct another statement that starts to feel a little bit more, as we could say, inferential. We could say there is a 95% probability that the population proportion P is within 2 standard deviations of P hat, which is equal to 0.54. Pause this video, appreciate that these two are equivalent statements. If there's a 95% chance that our sample proportion is within 2 standard deviations of the true proportion, well, that's equivalent to saying that there's a 95% chance that our true proportion is within 2 standard deviations of our sample proportion. And this is really, really interesting because if we were able to figure out what this value is, well, then we would be able to create what we could call a confidence interval. Now, you immediately might be seeing a problem. In order to calculate this, our standard deviation of this distribution, we have to know our population parameter. So pause this video and think about what we would do instead. If we don't know what P is, we don't know our population proportion, do we have something that we could use as an estimate for our population proportion? Well, yes, we calculated P hat already. We calculated our sample proportion. And so a new statistic that we can define is the standard error. The standard error of our sample proportions. And we can define that as being equal to, since we don't know the population proportion, we're going to use a sample proportion. P hat times 1 minus P hat, all of that over n. In this case, of course, n is 100. We do know that. It actually turns out, I'm not going to prove it in this video, that this actually is an unbiased estimator for this right over here. So this is going to be equal to 0.54 times 1 minus 0.54, so 0.46, all of that over 100. So we have the square root of 0.54 times 0.46 divided by 100. Close my parentheses, enter. So if we're around to the nearest hundredth, it's going to be actually around to the nearest thousandth. It's going to be approximately 5 hundredths. So this is going to be, this is approximately 0.05. So another way to say all of these things is, instead of, we don't know exactly this, but now we have an estimate for it. So we can now say with 95% confidence, and that will often be known as our confidence level right here, with 95% confidence between And so we want to go 2 standard errors below our sample proportion that we just happened to calculate. So that would be 0.54 minus 2 times 5 hundredths. So that would be 0.54 minus 10 hundredths, which would be 0.44. And we'd also want to go 2 standard errors above the sample proportion. So that would be that plus 10 hundredths. And 0.64 of voters support A. And so this interval that we have right here, from 0.44 to 0.64, this will be known as our confidence interval. And this will change not just in the starting point and the end point, but it will change the actual length of our confidence interval. It will change depending on what sample proportion we happen to pick for that sample of 100. A related idea to the confidence interval is this notion of margin of error. Margin of error. And for this particular case, for this particular sample, our margin of error, because we care about 95% confidence, so that would be 2 standard errors. So our margin of error here is 2 times our standard error, which is the 0.1 or 0.10. And so we're going 1 margin of error above our sample proportion, right over here, and 1 margin of error below our sample proportion, right over here, to define our confidence interval. And as I mentioned, this margin of error is not going to be fixed every time we take a sample. Depending on what our sample proportion is, it's going to affect our margin of error because that is calculated essentially with the standard error. Another interpretation of this is that the method that we use to get this interval right, the method that we use to get this confidence interval, when we use it over and over, it will produce intervals. And the intervals won't always be the same. It's going to be dependent on our sample proportion. But it will produce intervals which include the true proportion, which we might not know and often don't know. It will include the true proportion 95% of the time. I'll cover that information more in future videos. We'll see how the interval changes, how the margin of error changes. But when you do this calculation over and over and over again, 95% of the time, your true proportion is going to be contained in whatever interval you happen to calculate that time. Now, another interesting question is, well, what if you wanted to tighten up the intervals on average? How would you do that? Well, if you wanted to lower your margin of error, the best way to lower the margin of error is if you increase this denominator right over here. And increasing that denominator means increasing the sample size. And so one thing that you will often see when people are talking election coverage is, well, we need to sample more people in order to get a lower margin of error. But I'll leave you there and I'll see you.
Okay. That's it for tonight. There are more videos on there. Like, the homework for chapter 8 has already been posted on Connect. Please complete that. If you have any questions, you need detailed instructions to get complete, shoot me an email. I'll send you detailed solutions. Okay. I'll see you in 2 weeks. Of course, I think after next week we have a break, Thanksgiving, and then it'll be the week after that. I'll be here. Next week I'll be in Oxford. Okay. You'll have a good week. Thank you. Did you all hear that? Knoxville?
Yes.
You all have a good night. I'll see you next week in person. Take care.
See ya.
Bye.
Bye.